Hello and welcome to Sunny Treorchy for this edition of Mr. Roberts' online tutorials. This is the bridge prototype for Year 8. I started doing this by coming up with a basic prototype sketch. It changes along the way, so that's good to note. It's pretty standard really for design process. You're going to need a pencil or a pen, scissors, ruler, sellotape and about 20 sheets of paper. Now I started just rolling the paper up into tubes using a pen. Don't roll it too tight because you can't get the pen or the pencil out, or it's very difficult to get it out afterwards. You need to just sellotape the ends together once you've rolled them. Now, like I said, I used about 20. I made more as I went along because I really didn't know how big I wanted the bridge to be. The bridge is approximately 3 pieces of paper in length. Now it's tempting just to butt these 2 pieces together with a bit of sellotape, but what's going to happen is you're going to get a crease or a fold there, and that's going to be inherent weakness in the bridge. So what I decided to do was to trim or splice the 2 tubes together. Now I've done that, if you look closely, just by trimming the top and the bottom of the tube themselves and then inserting one into the other. Now you can sort of make the tubes different diameters, I suppose, so they just slot into each other, but you've got to sort of do some planning towards that. Make sure you've got enough tubes that are small, enough tubes that are a bit larger to take the other ones. And like I said before, I put 3 together. This comes to a distance of probably about 700 millimeters, and that makes the main girder then for the deck that goes across the bridge. So the main part of the beam bridge is the main girder that stretches across the deck, which is the road. The smaller tubes are 2 pieces of paper in length, and they are the top part of the frame of the bridge. So you have made an illustration with the different components of the bridge. As you can see, I color coded them. I'll go through them. Below the deck there is the substructure. The deck girder itself then is the long strut that goes across. The abutments are basically the anchor points where the bridge is sort of secured to either side of the span. The chord is the sort of outer sort of shape of the design, so including the ridge there. The struts help combat compression, so the squeezing pressure together or squeezing force, and the ties work against tension, so tension would be the pulling force. The superstructure is anything above the deck. So back to the design itself. I've marked the centers to my girders for the length, the ridge one for the top, and obviously the main girder at the bottom. This just helps me sort of map out where I want all my components for the superstructure that sits on top. Okay, so here I've got 1 piece of rolled paper lengthwise, and I've marked the center of that again, and I'm just going to crease the center of these to make the triangle shapes that are going to form my superstructure on the beams. Triangles are probably the strongest shape we use in engineering. They can't really be distorted in a natural sort of fashion. I mean, if you had a square and you push it on its side, you imagine to push it on its side, it becomes a rhombus. But with a triangle, you can't really compress it into another shape because it hasn't got many hinge points. So let me explain that a little bit. With a square, for example, if you push any of the corners, you find that the shape skews quite easily, and that creates lots of weak points. When creating structures, we like to use triangles because they are considered the strongest shape. See, if you skew them or try to sort of bend it out of shape, it retains the shape as a triangle. You'll find this with other shapes as well. You'll find that there's not much of an inherent structural advantage to them. We can use hexagons, pentagons, octagons, whatever shape you like really for the basic shape of your structure, but you need to introduce triangles to the shape or the form to introduce the strength. So back to the bridge itself, I've made some components here for the superstructure. They've been bent in half, so I can basically put them up against my two girders to see where I'd want these triangles to be introduced onto the model. I started in the center of my main girder and placed two triangles opposite each other in a symmetrical fashion. If you have symmetry, you have strength in design, so try to keep your superstructure as symmetrical as possible. I've continued that design then to the edge of the girder to create a sort of lattice shape. I just attached the top or the ridge girder to that design then, so that's consolidated the whole design together. I've made another one that's exactly the same, and at this point I think I used 18 pieces of paper. If you haven't got normal printing A4 paper, you could try this with newspapers or any other types of sort of junk mail you've got around the house. It'd be interesting to see what you guys use actually to have a go at this project at home. I've sellotaped both the ridge girders together then to make the entire superstructure for the design. So at this point now I've used graph paper and I've rolled it the same way, but I cut it into thirds, and I wanted to use different colour paper but I didn't have any, so I used graph paper just to illustrate how these different components work. I've cut these in thirds like I said, so they're a little bit smaller than the large lengths, and I've used them to sort of reinforce the superstructure, so I put one at either end of the deck. So these small component parts going across the riser girders going up and down are called struts. Now struts work to reduce the compression of the bridge. So if you imagine, if you pull down on the bottom of this bridge, the V shape at the bottom, there's going to be some compression across those triangles as they rise up. So these parts are just going to fight that action, squeezing them together. These parts I've put in, I've doubled them up, so these are like 1/6 the size of a normal piece of paper, half of the thirds, are called ties. Now the ties work against tension, so once that compression acts on the bottom, it's going to try and bend, so those parts are in place to try and reduce that bending in the bottom of the strut there. So there we are, that's the final product, 20 pieces of paper. It's good to try this with your family to sort of wind away the hours, or have a go with your friends online, see how much weight these bridges can take. The basic testing rig was set up in my garden. Excuse the silly Springer Spaniel in the background, he's far too curious. I used two chairs basically as the abutments for either end, and then I had to come up with some sort of way to sort of start hanging weights off of the centre of the bridge. So I thought I could use a colander for this. The colander itself weighed around 380, I think, grams. Each tin I weighed then to be around 460 grams. I checked out with another tin, and yeah, it was about 460 on the other one. I attached the colander to the centre of the bridge using an old drawstring from an old hoodie I found somewhere. So I just proceeded then to add tins. My bridge took the grand old total of 3 tins before it broke, so I could say that it was anywhere between I think 1,300 grams and 1,760 grams. Now, obviously, there are better ways of testing this bridge. I mean, I could have weighed other objects and slowly built it up, but for the purposes of the video, I thought I'd just use sort of consistent weights to do it. If you want to be a bit more accurate, like I said, you'd probably have to sort of use old style sort of weights, or measure, weigh different kitchen items in the house. Where it broke, you could see the main girder came apart, so there was a weakness in there. It structurally failed in the centre, which you would probably expect because that's the furthest point away from the abutment at the end of the bridge. So a general evaluation at the end of that, I would say that the strut and the tie that was introduced to the top definitely done its job. It just looks like it slipped there and allowed it to collapse. And also the connection of all the girders together needs to be improved, a little bit more sellotape, or just a better method of putting them together. So that's it really, guys. If you want to have a go with that and sort of feedback to us using Teams or using Twitter, that would be great. Thanks.